Gas stoichiometry. So, Avogadro strikes back. What is Avogadro mostly famous for? His number, which is
6.02 times 10 to the 23rd.
great. 6.02 times 10 to the 23rd, and that is how many? What in a mole?
1 mole.
How many particles? How many particles are in a mole? So that could be molecules, could be atoms, could be ions, could be FUs, formula units.
Oh.
Right? So he also did something else with gases. So Avogadro found that equal volumes of gases at the same temperature and pressure contain an equal number of particles. So what he did was he looked at 1 mole of helium gas and he compared it to 1 mole of iodine gas, which is diatomic. And what he found is at the same temperature and pressure, these had exactly the same volumes. All right. Why is this weird?
Because it's a lot lighter than
Right. All of you guys are right. Iodine is bigger than helium. So if iodine is bigger than helium, shouldn't 1 mole of it be taking up more space?
Yes. But it's not.
But it's not. We're going to talk about why. But first, he found that 1 mole of any gas at STP, so 1 atmosphere, 273 Kelvin, is 22.4 liters. We call this molar volume. Like molar mass is the number of grams in a mole. Right? Molar volume is how many liters 1 mole of gas takes up at STP. Now this only works at STP. If we're not at STP, we can't do this.
What did STP stand for again?
Standard temperature pressure. 273 Kelvin, 1 atmosphere.
Okay. So do we just like get rid of Celsius altogether?
Pretty much.
It's just annoying.
I mean, for gas laws, there's a lot of reasons why it's going to mess up your math. All right, so how is this possible? Now, the size of gas particles are so small relative to the massive size of their container that the difference between small and large gas particles doesn't actually change the volume. Remember, gases are mostly what? Empty space. So, when I have a slightly bigger molecule, I still have a large amount of empty space. So overall, my volume isn't going to change. So on the macroscopic level, 1 mole of gas, no matter what it is going to be 22.4 liters at STP.
So basically, if you change the atmospheric pressure, then everything just
If you change temperature or pressure, then it's not going to be 22.4 anymore.
Are we going to learn how to change all that?
You already have Charles' law and Boyle's law. Funny how that works. Okay. So if I had 2 moles of gas at STP, what volume would it be?
78.4.
No.
Oh, that I was
44.8.
44.8 liters. What if I had half a mole of gas?
Then you have 11.2.
11.2 liters. So this is just dimensional analysis. Right? So if I had 3 moles of gas at STP, what is the volume? So just like molar mass, right, you have 1 mole and then however many grams. Molar volume is 1 mole and then the 22.4 liters. So 3.5 moles times 1 mole over 22.4 liters. The moles cancel. So 3.5 times 22.4 gives me 78.4 liters.
Is it always going to be set up
I
like
mean,
it's always going to be the liter over the mole?
no, because if you're going from volume to moles, you'd have to flip it. Okay, another example. What is the volume of 44 grams of oxygen at STP? Now, I can't do anything with grams. I need molar volume, which means I need moles. Now, to go from grams to moles, I need molar mass. So, oxygen has a molar mass of what?
32,
Well, just oxygen.
12,
16. 16 times 2 is 32. So 44 grams, grams on the bottom, 32 grams in 1 mole, and every 1 mole is 22.4 liters. Notice your grams cancel, your moles cancel, you're left with liters. So 44 divided by 32 times 22.4 gives you 30.8 liters. So now with this new millimolar conversion, we can apply stoichiometry in a new way.